According to IBM, 90% of the data in the world today has been created in the last 2 years alone. By 2020, it's estimated that 1.7 megabytes of new information will be created every second for every human being on the planet. To put that into perspective, imagine every human being on Earth writing a book as long as the Bible every 2.5 seconds. With so much information readily available at our fingertips, how do we make sense of it all? Welcome to Information Overload, where we explore the strategies used by humans and machines in the field of data science and machine learning to do just that. Hello everyone, I'm Raymond Willie, and welcome to the first vlog post of Information Overload. This video is meant as a follow-up to my first blog post, so if you've not read it, I would recommend checking that out first. Now, you may remember in that post, I introduced a framework not just for communication, but for thinking. When we are dealing with vast amounts of data and complex analyses, we can use this framework as a way to organize our thought processes around the results and easily identify which pieces of information are most relevant to various stakeholders. To see this framework in action, we're going to walk through a sample data analysis and examine which pieces of information are best for technical reviews and which are best for non-technical presentations. For this scenario, let's imagine we are working with a hospital that is trying to better prepare for the types of critical patients it will see in the next 10 to 20 years. They want to know what the leading cause of death is right now and whether or not that is expected to remain the same in the future. These answers will help hospital administrators determine which types of doctors they should hire and how they should prioritize research. Unfortunately, we don't yet have the proper access to hospital records, so for the initial analysis, we have to work with public data. Fortunately, we were able to find a dataset from the National Center for Health Statistics, which focuses on the leading causes of death in the United States. It includes the total number of deaths by cause and state from 1999 through 2016. To calculate the death rate, which will be our target variable, we also need to incorporate state population data over the same time period. U.S. Census data provides this information on limited time intervals, and for now, we'll assume straight-line population growth between those intervals. Now, we also want to start exploring independent variables that may impact death rates, such as wealth and population density. So we're also going to bring in land area by state and use total GDP by state as a proxy for wealth. State and year can be used jointly as a primary key to link these data sets together. Let's pause here for a moment and think about the relevance of the information on this slide. Did we really need to go into that much detail? The answer, of course, is it depends on the audience. If we refer back to our framework, we can say that the specific makeup of the data sources represent our observations. We then applied a mapping methodology to link all of the data together. So we have observation and we have action, but we've not yet gone to insight. So the information here will be of great interest to a technical person reviewing the work, but the hospital administrator who is looking for actionable intelligence may or may not care about the details and how you came to your conclusions, provided that individual trusts that robust practices and checks are in place. For that type of presentation, it might be best to throw this slide into the appendix as reference should there be any questions about the methodology, but you don't want to get rid of it altogether. So, moving on, based on our analysis of available data, what we found was that among the top 10 causes of death, Heart disease and cancer claim the highest percentage of lives at 27% and 24% respectively. Unlike the previous slide, this one is more heavily geared towards the non-technical presentation. But before moving on, a technical person is likely to inquire about significance. How do we know the difference in death rates between heart disease and cancer are significant and not due to random chance and sampling? In this case, the simple answer is that we are working with population data. But for demonstration purposes, let's pretend this is sample data. Now, for a technical presentation, this is a type of question which is par for the course, and you should expect to have to address it. But for the non-technical presentations, you should still at least be prepared just in case. So let's have a look at what this slide might look like for a technical review. Here, you can see that a hypothesis test was performed to make the determination. The default assumption is that the difference is due to random chance and that the average death rate for cancer is not less than or equal to the death rate for heart disease. And we want to disprove this assumption with a 95% confidence level. We performed an F-test to compare variances, and based on the resulting p-value lower than 5% alpha, we can determine that the variances are unequal. This allowed us to perform the appropriate t-test and compare the means. The resulting p-value here is 0.00297, which allows us to say we are 95% confident that the difference in means is not due to random chance. So, knowing that heart disease has been the leading cause of death in the US since 1999, what is the trend? Has this rate been increasing or decreasing? Here, we can present a nice visual for managers to see the change over time. Red and orange states represent the highest percentages of deaths from heart disease, while green represents the lowest. Over time, we can see that many of the orange and red states turn green, and we see that the overall rate has dropped. Here again, we should be prepared for the question of whether or not the change is statistically significant. This is a pattern you will want to be aware of. In non-technical presentations, you should present visuals front and center that make it easy for the audience to grasp the findings. Keep the evidence for those findings in the appendix to provide additional justification if needed. For a technical review, however, you should be focusing on slides like this one, which present helpful visuals, but put greater focus on your methodology, observations, and actions. Here is one last example using regression analysis. We are looking at the relationship between population density and heart disease, as well as GDP per capita as a proxy for wealth against heart disease. The visuals here show the story pretty well on their own. As population density increases, we see rate of heart disease increase as well. And as wealth grows, we see rates decrease. But a technical reviewer is going to want to see greater levels of precision to justify the findings. In the graphs alone, we can see that a relationship exists, and we can see that it's relatively weak. With the full data from our regression model, we see p-values lower than 1%, which confirm the existence of a relationship. However, the adjusted R-squared number tells us that really only about 38% of the variance in death rates can be explained by population density and GDP per capita. So there are many other factors, or at least one other very significant factor at play in this regard. At this point, I think you get the idea. For the purposes of this video, we don't need to dive 6 feet under into the data, but you should probably have a good idea of where we could go next. And this brings us to features, functions, and benefits, which I like to collectively think of as recommendations. Now, you may be wondering how we're going to cover this part if we aren't making any specific recommendations for the hospital yet. The thing is, data science and analysis can be a lot like tugging at a thread. Sometimes you find something at the end right away, but other times it seems like a never-ending string. And there's an art to finding the right balance, which means that oftentimes your recommendations will actually be next steps. In this case, we can replace feature with recommendation and function with objective. You'll notice that when recommending next steps, you're actually making recommendations to seek new observations, take new actions, and gain new insights. As such, in this context specifically, this portion should be included in technical presentations as well. As an example, one recommendation might be to examine regional economic trends. The objective will be to predict whether the local economy is going to grow or shrink. Given the relationship between GDP and heart disease, the benefit would be an improved ability to determine whether we can expect deaths related to heart disease to continue their downward trend, or whether we can expect a change in the local trend over time. We might also recommend performing a deeper dive on cancer, similar to what we did with heart disease. By comparing and contrasting the results, we can get a better sense of whether heart disease will continue to be the leading cause of death, and if future planning and resources should be reallocated to prepare for newer trends. Lastly, we might also want to recommend incorporating hospital data into this data set in order to more effectively identify localized predictors of heart disease. Doing so could potentially allow us to improve the precision of the regression model and make more precise recommendations in the future. Now you'll notice there's not much detail to go into on this slide. And the reason for that is that if you have properly presented and supported your findings, they will do the heavy lifting and your recommendations will feel like a natural extension of them. The most important part of this is to make sure each recommendation is clearly tied to a specific insight or finding. Now, whether you choose to present all recommendations at the end or present each one with its corresponding finding really depends on the nature of your analysis. When all findings are focused on a singular problem or objective, as in our sample scenario, it is a good idea to save all recommendations for the end so as not to interrupt the broader narrative. On the other hand, if you are presenting a broad range of analyses that are more or less independent of each other, the groupings of recommendations should reflect that. In the end, our goal is to make sure that our target audiences understand the value of our work as it relates to their needs. They need to trust that the information we are providing is not only accurate, but relevant. Following this framework will help to ensure that you are able to cover both of these points for any given audience. With that, I hope you found this video useful. In future posts, we will get more technical and look at more advanced analytic techniques, but I thought starting off with this would give you a sense of how I operate and approach data science and analytics. Be sure to keep an eye out for my next post, where we'll perform a few hypothesis tests to answer questions about our data using two of the more fundamental tools for data science, SQL and Python.